The proton is one of the most familiar particles in the universe. It sits at the heart of every atom. It has a property called spin, a fixed, measurable quantum number that never changes. Spin 1/2, always. And for decades, physicists thought they understood exactly where that spin came from. A proton is made of 3 quarks. Each quark has its own spin. Add them up the right way, and you get spin 1/2. Simple, elegant, case closed. Except it wasn't. In 1988, an experiment at CERN measured how much of the proton's spin actually comes from its quarks, and the answer was almost none. The 3 quarks that supposedly explained everything contributed barely any of the spin at all. The physics world called it a crisis. And more than 3 decades later, the full answer is still being pieced together. If you find this kind of deep dive into the hidden structure of matter interesting, a quick like or subscribe genuinely helps the channel grow. It's a small thing, but it means a lot. Now, let's begin. Let's start with something fundamental. You exist because of protons. Every atom in your body has them. The hydrogen in the water you drink has a single proton at its core. The oxygen you breathe has 8. The carbon that forms the backbone of every biological molecule in your cells has 6. Protons sit at the center of every atom of every element on the periodic table. They are among the most common and most important particles in the visible universe. Without protons, atoms could not exist. Without atoms, there would be no chemistry. Without chemistry, there would be no stars, no planets, no oceans, no life. The proton is as basic to the structure of the physical world as anything in science gets. And every proton in existence carries a property called spin. Spin is a quantum mechanical quantity. It is measured, it is precise. And for the proton, its value is 1/2. Always. That number does not fluctuate. It does not depend on temperature, on pressure, or on where the proton happens to be. Whether a proton sits quietly inside a hydrogen atom drifting through deep space, or whether it has been accelerated to 99.9% of the speed of light inside a particle collider, its spin is 1/2. This value is as fundamental to the proton's identity as its mass or its electric charge. It is permanent, fixed, and absolute. For decades, physicists believed they knew exactly where this spin came from. The explanation was simple, elegant, and deeply satisfying. A proton is made of 3 quarks. Quarks are smaller particles that combine to build protons and neutrons. Each quark carries its own spin of 1/2. Combine the 3 quark spins according to the rules of quantum mechanics, and you get a total spin of 1/2 for the proton. 2 quark spins point one way, 1 points the other. The arithmetic is clean. The prediction matches observation. This was the textbook answer. It was taught in universities worldwide. It appeared on graduate qualifying exams. It was considered settled science. And then, an experiment showed it was almost entirely wrong. But before we get to that experiment and the shockwave it sent through physics, we need to understand something crucial first. We need to understand what spin actually is. Because spin is one of the most profoundly misunderstood concepts in all of science, and grasping it correctly is essential to understanding why the proton spin puzzle runs so deep. When you hear the word spin, your brain immediately reaches for something familiar. A top twirling on a table, a basketball rotating on a fingertip, a figure skater pulling her arms in and whirling faster, the Earth turning on its axis once every 24 hours, giving us day and night. These are all examples of rotation, of what physicists call classical angular momentum. An object has mass. That mass moves in a circular path around some axis. The faster it rotates, or the more massive it is, or the farther the mass sits from the axis of rotation, the greater its angular momentum. You learned about this in school. You can see it happen in front of you. You can reach out and stop a spinning top with your hand. You can speed up a merry-go-round by pushing it. You can slow down a bicycle wheel by squeezing the brake. Classical angular momentum is intuitive. It follows rules that match your everyday experience of the world. Quantum spin is not this. This needs to be stated as clearly as possible because the confusion between quantum spin and classical rotation causes more misunderstanding than almost anything else in physics. When physicists say the proton has spin 1/2, they do not mean the proton is a tiny ball physically turning on an axis. The proton is not spinning. There is no little sphere rotating. There is no surface moving. There is no axis you could stick a pin through. As far as every experiment in history has been able to determine, fundamental particles like quarks and electrons behave as mathematical points. They have no measurable internal size. They have no parts arranged in space that could revolve around each other. There is nothing there to spin in any classical sense. And yet the angular momentum is real. It is measurable. It produces concrete physical effects that are detected in laboratories around the world every single day. Spin creates magnetic fields. An electron with spin 1/2 acts as a tiny magnet. A proton with spin 1/2 also acts as a tiny magnet. These magnetic properties are not hypothetical. They are the basis of magnetic resonance imaging, the technology used in hospitals everywhere to scan the inside of your body. When you lie inside an MRI machine, a powerful magnetic field interacts with the spins of the hydrogen protons in the water molecules in your tissues. The protons absorb and re-emit radio waves in ways that depend on their spin states and their chemical environment. The machine detects those signals and builds a detailed image of your organs, your brain, your bones. Every MRI scan ever performed relies on the fact that protons have spin. If proton spin were not real, MRI would not work. The technology would be impossible. So spin is not classical rotation, but it is absolutely real angular momentum with measurable physical consequences. It is an intrinsic property of particles. It exists because the mathematics of quantum mechanics demands it. It interacts with magnetic fields the way angular momentum should, but it does not correspond to any physical rotation you could visualize. It simply is. It is a property with no classical analogy, and that is something you have to accept if you want to understand the quantum world. Spin was discovered experimentally before anyone had a theoretical framework to explain it. And the discovery came from one of the most important experiments in the history of physics. In 1922, two German physicists, Otto Stern and Stern-Gerlach, set out to test whether atoms carry angular momentum, and if so, how that angular momentum behaves when placed in a magnetic field. Their setup was ingenious. They heated silver to create a beam of silver atoms and sent that beam through a carefully shaped, non-uniform magnetic field, one that was deliberately stronger on one side than the other. If the atoms carried angular momentum, the magnetic field would push on them, deflecting them from their straight-line path. The direction and amount of deflection would depend on how the angular momentum was oriented. Classical physics made a specific prediction about what should happen. If angular momentum can point in any direction, which it certainly can for a rotating object like a spinning top, then different atoms in the beam would have their angular momentum pointed in all sorts of random directions. Some would be tilted up, some down, some sideways, some at every angle in between. The result should be a smooth, continuous smear of atoms across the detector, a broad band. Every possible deflection angle represented, with no gaps, no special positions, just a continuous spread. That is not what Stern and Gerlach found. Instead of a smooth smear, the beam split into exactly two discrete spots on the detector, one spot above the center line, one below. Nothing in between. No atoms landed at intermediate positions. The angular momentum of those silver atoms was not pointing in random directions across a continuous range. It was quantized, It could only take one of two specific values relative to the magnetic field, either aligned with the field or directly opposed to it. No other orientations existed. This was extraordinary. Nothing in classical physics predicted this behavior. A spinning top can lean at any angle. A gyroscope can tilt continuously through every possible orientation. But at the atomic scale, the rules were fundamentally different. Angular momentum was restricted to fixed, discrete values. It behaved like a switch with only two positions, not a dial you could turn smoothly. The experiment revealed something profound about nature. At the quantum level, angular momentum does not come in a continuous range. It comes in specific, countable, indivisible units. What Stern and Gerlach had discovered, though they did not fully understand it at the time, was the physical effect of quantum spin. The outermost electron in a silver atom has spin 1/2, and when you measure a spin 1/2 particle's orientation along any chosen axis, you only ever get one of two results: plus 1/2 or minus 1/2. Nothing else. Never 0, never 1/3, never some arbitrary fraction. Always and only one of exactly two values. This two-valuedness is not a limitation of measurement equipment. It is not something that better technology could overcome. It is a fundamental property of the quantum world, built into the mathematical structure of reality itself. The spin value is described by a quantum number. For electrons, protons, neutrons, and quarks, that quantum number is 1/2. The actual magnitude of the intrinsic angular momentum is 1/2 times a fundamental constant called h bar, which is Planck's constant divided by 2 pi. This value is locked in permanently. It cannot be increased. It cannot be decreased. It cannot be altered by any physical process whatsoever. From the moment a particle comes into existence until it ceases to exist, its spin quantum number remains fixed. It is as unchangeable as the particle's identity itself. And this fixed value has enormous consequences for how particles behave. Particles with half-integer spin, values like 1/2, 3/2, or 5/2, belong to a category called fermions. They obey a rule called the Pauli exclusion principle, formulated by the Austrian physicist Wolfgang Pauli in 1925. The principle states that no two identical fermions can occupy exactly the same quantum state at the same time. This single rule explains a staggering amount of physics. It explains why the periodic table of elements has the structure it does. Electrons in an atom must stack up into progressively higher energy levels because they cannot all crowd into the lowest level with the same spin orientation. This stacking determines every element's chemical properties. It determines which elements are metals and which are gases. It determines how atoms bond together to form molecules. The entire discipline of chemistry is, at its root, a consequence of the fact that electrons have spin 1/2 and obey the Pauli exclusion principle. Without quantum spin, there would be no chemistry. Without chemistry, there would be no biology. Without biology, you would not be here. Particles with integer spin, values like 0, 1, or 2, belong to a different category called bosons. Bosons follow entirely different rules. They compile into the same quantum state without any restriction. Photons, the particles of light, are bosons with spin 1. This is why lasers work. You can put trillions upon trillions of photons into exactly the same quantum state, all vibrating in lockstep, producing the intense, coherent light that makes laser technology possible. The Higgs boson has spin 0. Gluons, the particles that carry the strong force inside protons, are bosons with spin 1. The distinction between fermions and bosons, between half-integer spin and integer spin, is one of the deepest and most fundamental divisions in all of particle physics. Every particle in the universe falls into one of these two categories, and which category it belongs to determines almost everything about how it behaves. The proton is a fermion. its spin is 1/2. This has been confirmed by countless experiments over many decades, measured with extraordinary precision. It is one of the most firmly established facts in particle physics. No experiment has ever measured anything different. Now comes the deeper question. We know the proton has spin 1/2, but the proton is not a fundamental particle. It has parts. It has internal structure. And so the spin of the proton must somehow arise from whatever is going on inside it. The total spin has to come from somewhere. The question is where? In 1964, two physicists, Murray Gell-Mann and, independently, George Zweig, proposed that protons and neutrons are not elementary objects. They are built from smaller particles that Gell-Mann named quarks. A proton contains 3 quarks. Specifically, 2 up quarks and 1 down quark. The up quarks carry an electric charge of +2/3, and the down quark carries a charge of -1/3. Add up those charges, +2/3, +2/3, -1/3, and you get +1. That matches the proton's known charge exactly. The quarks are bound together by the strong force, one of the 4 fundamental forces of nature, and that force is carried by particles called gluons. The full theory describing how quarks and gluons interact is called quantum chromodynamics. Each quark is a spin 1/2 particle, just like the electron. So inside the proton, there are 3 spin 1/2 objects. The proton's total spin is also 1/2, and this sets up what seems like a straightforward question. How do 3 spin 1/2 values combine to produce a total of 1/2? In quantum mechanics, angular momentum addition follows precise mathematical rules. When you combine 2 spin 1/2 particles, their individual spins can either align, producing a combined spin of 1, or they can oppose each other, producing a combined spin of 0. These are the only 2 possibilities. Now add the third spin 1/2 particle. If the first 2 combined to give spin 1, adding another spin 1/2 can produce a total of either 3/2 or 1/2. If the first 2 combined to give spin 0, adding spin 1/2 gives only 1/2. The mathematics of quantum angular momentum coupling shows that 3 spin 1/2 particles can produce a total spin of either 3/2 or 1/2, depending on how the individual spins are oriented relative to each other. The proton has spin 1/2, not 3/2. This is important. There does exist a particle made of the same types of quarks with spin 3/2. It is called the delta baryon, and it is heavier and far less stable than the proton. It decays in roughly a trillionth of a second. The proton, by contrast, is stable. In the proton's configuration, the 3 quark spins arrange themselves so that 2 effectively cancel, and the remaining one gives the proton its net spin of 1/2. The arithmetic is clean. The quantum mechanics is consistent. The prediction matches the measured value perfectly. For more than 20 years, this was the accepted answer. The proton's spin comes from its quarks. The 3 quark spins combine to give spin 1/2. It was printed in textbooks. It was taught in classrooms. And the broader successes of the quark model reinforced the confidence enormously. The model correctly predicted the electric charges of dozens of hadrons, the particles made of quarks. It predicted patterns in their masses. It predicted the proton's magnetic moment, the strength of the tiny magnetic field it generates, to within a few % of the measured value. It predicted the ratio of the proton's magnetic moment to the neutron's magnetic moment almost exactly. With so many successful predictions, nobody had much reason to doubt that the quark spin picture was essentially correct. The magnetic moment deserves a moment of explanation, because it connects directly to spin. Any charged particle with angular momentum generates a magnetic field. It acts like a tiny bar magnet with a north pole and a south pole and a specific strength. The strength of that magnetic field is called the magnetic moment, and it depends on two things: the particle's charge and its angular momentum, specifically its spin. A particle with more spin or more charge produces a stronger magnetic field. For a point like spin 1/2 particle like the electron, quantum electrodynamics predicts the magnetic moment with breathtaking precision, matching experiments to better than 10 decimal places. It is one of the most accurate predictions in all of science. For the proton, the situation is different. The proton is not a point particle. It has internal structure. Its magnetic moment depends not just on its total spin, but on how that spin is distributed among its internal constituents, and on how those constituents are charged. In the simple quark model, the calculation is elegant. Each quark carries a fraction of the proton's charge and contributes to the magnetic moment according to its own spin orientation. The up quarks, with their positive charge, and the down quark, with its smaller negative charge, generate magnetic fields that partially cancel. The result is a net magnetic moment that the quark model predicted to within roughly 7% of the measured value, which, for a calculation involving no free parameters beyond the quark charges and spins, was considered remarkably good. Getting the magnetic moment approximately right meant the model was correctly describing both the charges and the spin orientations of the quarks simultaneously. It reinforced the confidence that quark spins were the whole story. But the simple quark model made a critical assumption. It assumed that the 3 quark spins are the entire story. 100% of the proton's spin comes from quark spins. Nothing from gluons. Nothing from the orbital motion of quarks inside the proton. Nothing from the sea of particle-antiparticle pairs that the full theory says must exist in the proton's interior. Just 3 quarks, their spins neatly arranged. This assumption kept the math simple and the predictions accurate enough to seem convincing. But the inside of a proton is nothing like 3 little balls sitting still in empty space. If you could somehow peer inside a proton, what you would find is closer to a storm than a structure. The proton is roughly 1 femtometer across. That is 1 quadrillionth of a meter, about 100,000 times smaller than an atom. And inside that unimaginably tiny volume, the strong force is driving something extraordinary. The strong force is the most powerful of the 4 known fundamental forces of nature. At the distances relevant inside a proton, it is roughly 100 times stronger than the electromagnetic force. And it has a property that sets it apart from every other force. It gets stronger as you try to pull quarks apart. Imagine stretching a rubber band. The farther you stretch it, the harder it resists. The strong force is like that, except far more extreme. If you tried to separate a quark from the other quarks inside a proton, the energy stored in the stretching force field would eventually become so large that it would create entirely new quarks and antiquarks from the vacuum. The energy converts into mass. New particles appear. You never isolate a single quark. This phenomenon is called confinement. No free quark has ever been observed, and the theory says none ever will be. The particles that carry the strong force are called gluons, and gluons are remarkable. Unlike photons, which carry the electromagnetic force but have no electric charge themselves, gluons carry the strong force, and they themselves carry the strong force's type of charge, called color charge. This means gluons interact with each other. They do not simply shuttle passively back and forth between quarks, like messengers delivering letters. They emit more gluons. They split into pairs of quarks and antiquarks. They absorb each other. They merge. The interior of the proton is a violently dynamic quantum environment. Gluons are constantly being created and absorbed. Quark-antiquark pairs flicker into existence, and annihilate each other in timescales so short that no instrument can capture them. At any given instant, the proton contains far more than just three quarks. It holds a churning sea of gluons and temporary quark-antiquark pairs, all interacting furiously, all carrying energy and momentum and angular momentum. This is the real environment inside the proton. This is the system from which spin 1/2 must emerge. And here is something that makes the puzzle even more striking. Most of the proton's mass does not come from its quarks. The up quark has a mass of only about 2 million electron volts. The down quark has a mass of about 5 million electron volts. 2 up quarks and 1 down quark add up to roughly 9 million electron volts of quark mass. But the proton's total mass is about 938 million electron volts. The quarks account for less than 2% of what the proton weighs. More than 98% of the proton's mass comes from somewhere else entirely. It comes from the energy of the gluon field and from the kinetic energy of quarks and gluons moving around inside the proton at enormous speeds. Through Einstein's equivalence of mass and energy, all that energy manifests as mass. The proton is, in a very real and measurable sense, a bound state of energy. The quarks provide the quantum numbers, the identity, the electric charge, the flavor. But the vast majority of what makes a proton massive is the strong force itself, the gluon field, and the frantic motion it sustains. Think about what that implies for spin. If more than 98% of the proton's mass comes from gluons and the motion of quarks, rather than from the quarks themselves, why would anyone expect 100% of the proton's spin to come from quark spins alone? In retrospect, this question should have been asked much earlier. The assumption that quark spins account for everything was always an oversimplification. But the simple quark model's track record was so impressive that the assumption went largely unquestioned for decades. The tool that would finally put this assumption to a direct experimental test is called deep inelastic scattering. It is one of the most powerful and important techniques ever developed in particle physics, and it works on a beautifully simple principle. You take a beam of high-energy particles, typically electrons or muons, and fire them at protons. When an incoming particle approaches a proton, it interacts through the electromagnetic force by exchanging a virtual photon, a quantum of electromagnetic energy that flashes into existence for the briefest instant during the collision and then vanishes. If that virtual photon carries enough energy, it can resolve the individual quarks inside the proton. The higher the energy, the finer the detail you can see. By carefully measuring the scattered particles as they emerge, what angles they fly off at, how much energy they lose, how their trajectories change, physicists can reconstruct what the quarks were doing inside the proton at the precise moment of the collision. Deep inelastic scattering experiments at the Stanford Linear Accelerator Center in the late 1960s and early 1970s provided the first direct evidence that quarks are real physical entities inside the proton. The experiments showed that the proton contains hard, point-like constituents carrying fractional electric charges, exactly as the quark model predicted. Quarks were not merely mathematical devices useful for organizing particle data. They were real objects, physically present inside real protons. But deep inelastic scattering can reveal far more than the mere existence of quarks. By using polarized beams and polarized targets, meaning beams where the particle spins are deliberately aligned in a known direction, and protons whose spins are likewise aligned, you can extract something far more specific. You can measure what fraction of the proton's total spin is carried by the spins of the quarks inside it. The method works because the probability of a particular scattering event depends on the relative alignment of the incoming particle's spin, the target proton's spin, and the spins of the individual quarks being struck. By comparing scattering rates across different spin combinations, experimenters can tease out the quark spin contribution. The experiments are extraordinarily difficult. They require intense beams, precisely polarized targets held at cryogenic temperatures, and sophisticated detectors capable of measuring scattered particles with extreme accuracy. But the physics is sound. The technique works. And in the 1980s, a team of physicists set out to do exactly this. Their collaboration was called the European Muon Collaboration, and they conducted their experiment at CERN, the great particle physics laboratory straddling the border of France and Switzerland near Geneva. The physicists fired a beam of polarized muons at polarized proton targets and carefully measured the scattering. They knew the expected answer. The textbook said quark spins carry essentially all of the proton's spin. The experiment was meant to confirm this, to put a precise number on a quantity everyone believed was already understood. It was supposed to be a validation of settled knowledge, a measurement of a known result. What they found instead left the physics community stunned. The result was so unexpected, so far from what the textbooks predicted, that it earned a name usually reserved for events of far greater drama. They called it a crisis. The first reaction from much of the community was disbelief, not polite skepticism, genuine disbelief. Experimentalists questioned the data. Were the polarizations of the beam and target measured correctly? Polarization is notoriously difficult to calibrate. If the muon beam was less polarized than the experimenters believed, or if the target proton polarization was overestimated, the extracted quark spin fraction would be artificially suppressed. The EMC team had been meticulous, but the result was so far from expectations that many physicists assumed there had to be a mistake somewhere in the chain of measurement. Others questioned the extrapolation. The EMC measured the spin-dependent scattering function over a specific range of quark momentum fractions, but the sum rule requires integrating over the entire range, from 0 to 1. The experiment could not cover the very lowest and very highest momentum fractions. To complete the integral, the experimenters had to extrapolate, extending their measured curve into regions where they had no data, using theoretical models to guide the extension. Critics argued that the extrapolation was unreliable, that the unmeasured regions might contain large contributions that would bring the result back in line with expectations. If there were a large positive contribution from very low momentum fraction quarks, the crisis might evaporate. But as more experiments covered wider kinematic ranges, the extrapolation uncertainties shrank, and the result held. The quark spin fraction did not climb back to 60 or 100%. It stayed stubbornly low. On the theoretical side, the response was intense and creative. Dozens of papers appeared within months, each proposing a different explanation for the missing spin. One of the most important early responses focused on the assumption that had underlain the Ellis-Jaffe prediction. Ellis and Jaffe had assumed that strange quarks inside the proton are not polarized. Strange quarks are heavier than up and down quarks. They are not valence quarks. They exist only as part of the quark-antiquark sea, briefly created by gluon splitting and quickly annihilating back into gluons. It seemed reasonable to assume that these fleeting, heavy sea quarks would not carry any net spin alignment. They would pop in and out of existence too quickly and too randomly to contribute. The EMC result suggested otherwise. When theorists reanalyzed the data allowing for strange quark polarization, they found something unexpected. The data were consistent with the strange quarks being polarized in the opposite direction to the proton's spin. Strange quark spins appeared to be anti-aligned with the proton's overall spin, actively subtracting from the total rather than simply contributing nothing. This was deeply counterintuitive. Why would strange quarks, which are not even permanent residents of the proton, conspire to spin against it? The answer lies in the complex dynamics of the strong force. The gluon field that creates strange quark-antiquark pairs can preferentially produce them in specific spin states. The polarization of the gluon field imprints itself on the C quarks it creates. The C is not random. It is shaped by the same dynamics that shape everything else inside the proton. This raised a deeper question. If the original assumption about strange quarks was wrong, what else might be wrong? The Ellis-Jaffe sum rule was not a fundamental result of quantum chromodynamics. It was a prediction built on an assumption. Remove the assumption and the prediction changes. The more fundamental sum rule, the Bjorken sum rule, makes no assumption about individual quark flavors. It relates the difference between proton and neutron spin structure functions to a well-known coupling constant of the weak force, and it follows directly from the symmetry properties of quantum chromodynamics with minimal theoretical input. Testing the Bjorken sum rule became an urgent priority, because if it failed, the problem would not be a wrong assumption about strange quarks. It would be a failure of quantum chromodynamics itself, a far more serious crisis. Fortunately, subsequent experiments confirmed that the Bjorken sum rule holds to within a few percent, validating the theoretical framework and confirming that quantum chromodynamics was not broken. The crisis was not about the theory being wrong, it was about our assumptions being too simple. Another theoretical response involved a subtle feature of quantum chromodynamics called the axial anomaly. In quantum field theory, certain symmetries that exist at the classical level are broken by quantum effects. The axial anomaly is one such broken symmetry. It connects the quark spin measurement to the gluon field in a non-obvious way. Because of the anomaly, what the experiment measures as quark spin is not purely the intrinsic spin of the quarks. It contains a contamination from the gluon field, a term proportional to the gluon spin that subtracts from the apparent quark contribution. This means the measured quark spin fraction is not exactly the same as the true quark spin fraction. The gluon field partially masks the quark contribution, making it appear smaller than it actually is. How large this anomaly contribution is depends on the gluon spin, which at the time was completely unknown. Some theorists argued that the anomaly could account for much of the discrepancy, that quarks really do carry a substantial spin, but the gluon anomaly hides it. Others argued the effect was too small to explain the full deficit. The debate continued for years and was only partially settled when RHIC measured the gluon spin directly. The anomaly is real, and it does affect the interpretation, but it is not large enough to restore the naive quark model prediction. Even after accounting for the anomaly, quarks carry only a minority of the proton's spin. The European Muon Collaboration, known in the physics world simply as the EMC, published its results in 1988. The paper landed like a detonation. Before we examine what they found and why it was so shocking, let's understand exactly what they did and how the measurement worked. Because the technique is what made the discovery possible, and the precision of that technique is what made the result impossible to dismiss. Deep inelastic scattering had already proven itself as the most powerful way to look inside a proton. The early experiments at the Stanford Linear Accelerator Center in the late 1960s had confirmed that quarks were real. But those experiments used unpolarized beams and unpolarized targets. The protons in the target had their spins pointing in random directions, and the incoming particles were similarly random in their spin orientation. This is perfectly fine if you want to know what types of quarks exist inside the proton, how many there are, and what fraction of the proton's momentum each one carries. Unpolarized scattering tells you about the distribution of matter inside the proton, but it tells you nothing about how that matter is spinning. To measure spin, you need polarization. Polarization means controlling the direction of spin. When physicists say a beam of particles is polarized, They mean the spins of the particles have been deliberately aligned in a specific direction. Instead of pointing randomly in every possible orientation, most or all of the spins point the same way. Similarly, a polarized target is one where the protons inside the target material have their spins aligned. Achieving this is extraordinarily difficult. Proton spins in ordinary matter point in random directions because thermal energy constantly jostles them around. To force them into alignment, you need a combination of extremely powerful magnetic fields and extremely low temperatures, often less than 1 degree above absolute zero. You also need special target materials, typically compounds containing hydrogen, where the proton spins can be coaxed into alignment through a process called dynamic nuclear polarization. Building and maintaining a polarized target is one of the most technically demanding feats in experimental physics. The target must stay polarized for days or weeks while a beam of high-energy particles smashes through it continuously. The EMC experiment at CERN used a beam of polarized muons. A muon is essentially a heavier cousin of the electron. It has the same electric charge and the same spin of 1/2, but it is about 207 times more massive. Muons are useful for deep inelastic scattering because their greater mass means they lose less energy to radiation as they pass through matter, which makes the measurements cleaner. The muon beam at CERN carried energies up to about 200 billion electron volts, high enough to resolve the individual quarks inside a proton with excellent precision. The beam was naturally polarized by the process that created it, which was a significant advantage. The target was a block of butanol, an organic compound rich in hydrogen, cooled to a fraction of a degree above absolute zero and subjected to a powerful magnetic field. The hydrogen nuclei in the butanol, which are simply protons, were polarized through dynamic nuclear polarization. At any given moment, roughly 70 to 80% of the proton spins in the target were aligned in the same direction. That is a remarkable degree of alignment for a target containing billions upon billions of protons. Here is how the measurement works in principle. You fire the polarized muon beam at the polarized proton target. When a muon passes close enough to a quark inside a proton, it interacts by exchanging a virtual photon. The virtual photon carries energy and momentum from the muon to the quark, and the muon ricochets off at a new angle with reduced energy. By measuring the angle and energy of the scattered muon, you can reconstruct what happened during the collision, what quark was struck, how much momentum it was carrying, and, critically, which direction its spin was pointing. The key insight is that the probability of the scattering event depends on the relative orientation of the spins. If the muon spin and the struck quark spin are aligned, pointing in the same direction, the probability of scattering is slightly different than if they are anti-aligned, pointing in opposite directions. This difference is small, but it is measurable. By comparing the scattering rate when the muon spin and proton spin are parallel with the scattering rate when they are anti-parallel, and doing this across a wide range of collision energies and scattering angles, physicists can extract a quantity that tells them how much of the proton's spin is carried by the spins of its quarks. The mathematical framework for this extraction is built on what are called sum rules. A sum rule is a relationship between a measured quantity, integrated over all possible collision conditions, and a fundamental property of the particle being studied. In the context of proton spin, the relevant sum rule connects the integral of a particular spin-dependent scattering function, measured across the full range of quark momentum fractions, to the total fraction of the proton spin that comes from quark spins. The derivation is rigorous. It follows from the basic principles of quantum chromodynamics and the symmetry properties of the strong force. The physics community had high confidence in the framework. The only question was what number the experiment would produce. In 1974, two theoretical physicists, John Ellis and Robert Jaffe, had derived a specific prediction for what this integral should be. Their calculation relied on a reasonable assumption. They assumed that the strange quarks inside the proton, the heavier quarks that pop in and out of existence as part of the quark-antiquark sea, are not polarized. Their spins should be randomly oriented and should not contribute to the proton's overall spin. Under this assumption, Ellis and Jaffe predicted that the quark spins should account for roughly 60% of the proton's total spin. Not 100%, because even in the 1970s, theorists understood that quantum chromodynamics corrections would reduce the naive quark model number somewhat. But still a substantial majority. The quarks should carry most of the spin. This was the prediction that the EMC set out to test. The naive quark model, the simplest version taught in introductory courses, predicted 100%. The more sophisticated Ellis-Jaffe prediction said about 60%. Both numbers were well defined, well understood, and considered reliable within the physics community. No serious physicist expected the experimental result to deviate dramatically from these predictions. The experiment was supposed to confirm what everyone already knew. It did not. The EMC measured the integral of the proton's spin-dependent scattering function across their accessible range and, after careful extrapolation to cover the full range, extracted the fraction of proton spin carried by quark spins. The number they found was roughly 12%, and the uncertainty on that number was large enough that it was statistically consistent with zero. Zero. The quarks, the three fundamental constituents that were supposed to carry essentially all of the proton's spin, appeared to carry almost none of it. The result didn't just disagree with the naive quark model prediction of 100%. It didn't just fall below the Ellis-Jaffe prediction of 60%. It was consistent with the quarks contributing nothing at all. The entire accepted picture of where proton spin comes from collapsed in a single measurement. The reaction in the physics community was swift and intense. Theoretical physicists scrambled to understand what had happened. Experimentalists questioned whether the measurement could be wrong. Papers flooded the journals. Conferences dedicated entire sessions to the result. The finding was so dramatic and so unexpected that it was given a name that captured the mood of the moment: the proton spin crisis. This was not a minor discrepancy. This was not a 10 or 20% deviation from the expected value. This was a result that said the foundational explanation for one of the proton's most basic properties was wrong. Not slightly off, not in need of a small correction, but fundamentally, drastically wrong. The three quarks that physicists had relied on for decades to explain proton spin turned out to carry only a small fraction of it. Something else was carrying the rest, and nobody knew what it was. Let's appreciate why this was so deeply unsettling. As we saw earlier, the quark model had compiled an extraordinary record of successful predictions across dozens of particles. Nothing in that record suggested anything was missing, and the spin predictions were among the model's proudest achievements, the results that physicists pointed to as proof that the model captured something deep and true about the structure of matter. The proton has spin 1/2. The neutron has spin 1/2. The delta baryon has spin 3/2. All of these followed naturally from combining three spin 1/2 quarks according to the rules of quantum mechanics. The predictions matched the data perfectly. Generations of graduate students learned this calculation as one of the most elegant results in particle physics. It was clean, it was correct, and it seemed complete. But matching the total spin value is not the same as correctly identifying where the spin comes from. The quark model predicted that three quark spins combine to give 1/2. That prediction is correct, but the implicit assumption that the quark spins are the only contribution was never really tested until the EMC experiment. The total spin is constrained by quantum mechanics. The proton must have spin 1/2. But the internal accounting, the question of what fraction comes from quarks and what fraction comes from other sources, is a separate question entirely. And that is the question the EMC answered. An analogy might help. Imagine a company has exactly $100 in revenue. You know this for certain because you have audited the total. Now suppose someone tells you that all $100 comes from product sales. You accept this because the company sells products and the number seems reasonable. But then you actually examine the books. You look at where the money comes from line by line, and you discover that product sales account for only $12. The other $88 comes from sources nobody mentioned: consulting fees, investment returns, licensing agreements, income streams that were ignored because the simple story seemed sufficient. The total is still $100. The audit was always correct. But the internal breakdown is completely different from what everyone assumed. That is essentially what happened with proton spin. The total is 1/2. That has never been in question. What the EMC revealed is that the internal accounting, the breakdown of where that 1/2 comes from, was utterly different from the accepted picture. The quarks contribute far less than expected. Other sources must make up the difference. Now, an extraordinary claim requires extraordinary evidence. One experiment, no matter how carefully designed, is not enough to overturn decades of accepted physics. The physics community demanded confirmation. And over the following years, that confirmation came, again and again, from multiple independent experiments using different beams, different targets, different detectors, and different laboratories. The SMC, or Spin Muon Collaboration, was a follow-up group at CERN that ran through the 1990s. It extended the EMC measurements with improved precision, covering a wider range of collision energies and quark momentum fractions. The SMC confirmed the EMC result. Quark spins carry a small fraction of the proton's spin. The number was refined upwards slightly from the original EMC value, but it remained far below the predictions of both the naive quark model and the Ellis-Jaffe calculation. At the Stanford Linear Accelerator Center, a series of experiments designated E142, E143, E154, and E155 used high-energy polarized electron beams instead of muons. These experiments measured spin-dependent scattering not just off protons, but also off neutrons, using targets containing helium-3 and deuterium. Neutrons, like protons, are made of 3 quarks, 2 down quarks and 1 up quark, and they also have spin 1/2. Measuring both protons and neutrons is important because the Bjorken sum rule, which we discussed earlier, requires data from both. The SLAC experiments were the first to test it with high precision, using both proton and neutron targets, and their results confirmed its validity, while simultaneously providing independent evidence that quark spins contribute far less than 100%. At DESI, the German particle physics laboratory in Hamburg, the Hermes experiment used a different approach. Instead of a solid polarized target, Hermes used a polarized gas target, a thin stream of polarized hydrogen or deuterium gas injected into one of the storage rings of the Hera accelerator. This technique had advantages. Gas targets are cleaner than solid targets. There are no complications from the nuclear environment of a solid material. The results are more straightforward to interpret. Hermes ran from 1995 through 2007, collecting an enormous dataset. Its measurements agreed with the other experiments. Quark spins carry a minority of the proton's spin. At CERN again, the COMPASS experiment began taking data in 2002 and continued for many years. COMPASS used an upgraded muon beam with higher intensity and improved polarized targets. Its measurements were among the most precise ever achieved for spin-dependent scattering. COMPASS confirmed and refined the picture that had been emerging for over a decade. The confirming experiments did more than simply repeat the EMC measurement with higher precision. They extended the picture in important ways. One key advance was the ability to decompose the quark spin contribution by quark flavor, determining separately how much spin is carried by up quarks down quarks, and strange quarks. This flavor decomposition revealed an interesting pattern. Up quarks tend to have their spins aligned with the proton's spin. They contribute positively. Down quarks tend to have their spins anti-aligned. They contribute negatively, partially cancelling the up quark contribution. And strange quarks, as the post-EMC analysis had suggested, also appear to have a small negative contribution, though the exact size remains debated, because strange quark measurements are the most difficult and carry the largest uncertainties. The net result of adding up and down and strange contributions is the roughly 30% total quark spin fraction. But that 30% is itself the result of significant internal cancellation. The up quarks contribute more positively than the total, and the down and strange quarks pull the number back down. The internal structure of even the quark spin contribution is more complex than a simple sum. By the early 2000s, the experimental situation was clear. Multiple independent experiments at different laboratories around the world, using different beam particles, different target types, different energies, and different detection techniques, all agreed. The fraction of the proton's spin carried by quark spins is approximately 25 to 33%. Not zero, as the original EMC result had tantalizingly suggested. The early measurement had large uncertainties, and as more data accumulated, the number settled to a value that is clearly not zero, but is also clearly far below what the quark model predicted. About a quarter to a third. Not 60%, not 100%, roughly 30%. This means that somewhere around 70% of the proton's spin comes from sources other than quark spins. 70% unaccounted for. In a particle that sits at the heart of every atom, in one of the most studied objects in all of physics. 70% of its most basic angular momentum property was missing from the standard explanation. Where does it go? Understanding the answer requires abandoning the simple picture of a proton as three quarks sitting still in a tiny container. That picture was always a cartoon. It was useful for organizing particles and predicting quantum numbers, but it was never meant to be taken as a literal description of the proton's interior. The real proton, the one described by the full theory of quantum chromodynamics, is a far more complex and dynamic object than three quarks frozen in place. And it is within that complexity that the missing spin is hiding. The first thing to recognize is a distinction physicists make between the three quarks that give the proton its identity and everything else inside it. Those three quarks, two up and one down, are called valence quarks. They carry the quantum numbers that distinguish a proton from a neutron. But as we saw earlier, valence quarks are not alone. They are immersed in the dense, energetic gluon field we already described, surrounded by the fleeting quark-antiquark pairs that field constantly generates. The crucial new point is that every one of those transient participants, every gluon, every C-quark, every momentary antiquark, can carry angular momentum. Not just energy and momentum, but angular momentum specifically. And that changes the spin accounting completely. This is the critical realization that the proton spin crisis forced upon the physics community. In the simple quark model, angular momentum was assigned only to the spins of the three valence quarks. Everything else was ignored. But the full theory of quantum chromodynamics demands that other contributions exist. The total angular momentum of the proton, its spin 1/2, is the sum of multiple terms. There are the quark spins, which the experiments showed account for about 30%. But there are also the spins of the gluons. Gluons are spin 1 particles. They carry intrinsic angular momentum just as quarks do. And inside the proton, there are many gluons at any given instant, far more gluons than quarks in terms of sheer numbers. The gluon field is dense and energetic. If even a modest fraction of the gluon spins are aligned, they could contribute substantially to the proton's total spin. Then there is orbital angular momentum. This is angular momentum associated not with the intrinsic spin of a particle, but with its motion through space. Quarks move inside the proton, and that motion can carry angular momentum just as a planet's orbit carries angular momentum around a star. Gluons move too, and they can carry orbital angular momentum of their own. The details of how this works inside a quantum system like the proton are subtle, and we will explore them properly in a moment. So the total spin of the proton is the sum of 4 contributions. First, the intrinsic spins of the quarks. Second, the intrinsic spins of the gluons. Third, the orbital angular momentum of the quarks. Fourth, the orbital angular momentum of the gluons. These 4 terms must add up to exactly 1/2. This is a firm requirement of quantum mechanics. The total is fixed. The question is how it is distributed among the 4 contributions. The EMC experiment and its successors measured the first term, quark spins, and found it to be about 30% of the total. The remaining 70% is distributed among the other 3 terms: gluon spin, quark orbital angular momentum, gluon orbital angular momentum. These are the reservoirs where the missing spin is hiding. But measuring these other contributions is far harder than measuring quark spins. The EMC technique, polarized deep inelastic scattering, is specifically sensitive to quark spins because the electromagnetic force, the force by which the incoming muon or electron interacts with the quarks, couples directly to electrically charged particles. Quarks have electric charge, so the virtual photon can strike them and reveal their spin orientation. But gluons are electrically neutral. They do not interact with photons. You cannot hit a gluon with a virtual photon the way you hit a quark. This means the standard deep inelastic scattering technique is essentially blind to gluon spin. Measuring the gluon contribution requires entirely different experimental approaches. Orbital angular momentum is even harder. It is not a local property of a single particle. It depends on how a particle's position and momentum are correlated, and measuring such correlations inside a system as small and fast-moving as a proton pushes the limits of what experiments can achieve. Accessing orbital angular momentum requires measurements of quantities called generalized parton distributions, which encode information about the spatial and momentum structure of quarks and gluons simultaneously. Extracting these distributions from scattering data is one of the most active and challenging areas of modern nuclear physics. The proton spin crisis did not mean that physicists had no idea where proton spin comes from. That would be an overstatement. The proton has spin 1/2. That fact was never in doubt. What was in doubt, what remains an active research problem, is the detailed internal accounting, the spin budget. How much comes from quark spins, how much from gluon spins, how much from quark orbital motion, how much from gluon orbital motion. The total is fixed at 1/2. But dividing that total among the 4 contributions with precision is one of the most difficult measurement challenges in all of physics. What the crisis really revealed is something deeper than a disagreement over numbers. It revealed that the proton, an object we had been studying for nearly a century, was far more complex than we had assumed. The simple 3-quark picture, while brilliant and enormously useful, captured only a fraction of the proton's true nature. The real proton is a many-body quantum system of quarks and gluons, bound together by the strongest force in nature, with its properties emerging from the collective behavior of all its constituents. Spin is not simply inherited from 3 quarks, the way eye color is inherited from parents. Spin emerges from the full quantum dynamics of the system, from every quark, every gluon, every fluctuation in the strong force field. And the effort to unravel that emergence, to trace exactly how spin 1/2 arises from the churning quantum interior of the proton, is one of the great ongoing quests in modern physics. A quest that has already demanded some of the most sophisticated experiments ever constructed, and that will soon enter a new era with facilities designed specifically to answer questions the EMC first raised more than 3 decades ago. So the proton spin is 1/2. The quarks contribute about 30% through their intrinsic spins. That leaves roughly 70% unaccounted for. 70% of the angular momentum of one of the most fundamental objects in the physical universe, hiding somewhere inside a volume smaller than a trillionth of a centimeter across. The question that consumed particle physics after the EMC result was brutally simple. Where is the rest? The answer, as physicists gradually came to understand, is that the missing spin is distributed across 3 other reservoirs: the intrinsic spin of gluons, the orbital angular momentum of quarks, and the orbital angular momentum of gluons. Each of these contributes to the proton's total angular momentum. Each of them is real. Each of them is, at least in principle, measurable. And together with the quark spins, they must add up to exactly 1/2. Not approximately, exactly. Quantum mechanics demands it. The total angular momentum of the proton is fixed by the deepest laws of physics, and every contribution, no matter how small or how difficult to measure, must be included in the accounting. Let's take these one at a time, starting with the one that attracted the most immediate attention after the crisis: gluon spin. Gluons are the carriers of the strong force. They are the particles that bind quarks together inside the proton. And like all particles in the quantum world, gluons carry intrinsic spin. But while quarks have spin 1/2, gluons have spin 1. They are bosons, not fermions. Their spin quantum number is a full integer, twice the value carried by a quark. Because gluons are massless, they carry only 2 physical spin orientations along any chosen axis, +1 or -1. There is no zero state. A massive spin 1 particle would have 3 orientations, but massless particles like gluons and photons are restricted to 2. Even so, each orientation carries a full unit of angular momentum, compared to only 1/2 for a quark. This means each gluon carries twice as much angular momentum per particle as a quark does, which makes the gluon spin contribution potentially very significant. But whether gluon spin actually contributes to the proton's total spin depends on something subtle. It depends on whether the gluon spins inside the proton are, on average, aligned. If the gluon spins point in random directions with no net preference, they cancel out. Some point in the +1 direction, some point in the -1 direction, and the average is nothing. The gluons would be there, carrying spin individually, but their collective contribution would vanish. This is the same principle that makes an unpolarized beam of particles carry no net angular momentum, even though each individual particle has spin. If the orientations are random, the total averages to 0. But if the gluon spins are even partially aligned, even if just a small surplus of gluons spin in one direction compared to the other, the net gluon spin contribution can be substantial. And inside the proton, there is no reason to assume the gluons are unpolarized. The proton is not a box of randomly arranged particles. It is a tightly bound quantum system held together by the strong force, and the dynamics of that force determine how every constituent behaves, including how their spins are oriented. So the question becomes an experimental one. Are the gluons inside the proton polarized? And if so, how much net spin do they carry? As we already established, the electromagnetic probe that revealed the quark spin crisis cannot see gluons at all. Gluons carry no electric charge, so virtual photons pass them by completely. To measure gluon spin, physicists needed an entirely different type of experiment, and they found one: proton-proton collisions. When two protons collide at very high energy, the interaction is dominated by the strong force, not the electromagnetic force. The quarks and gluons inside one proton interact directly with the quarks and gluons inside the other. And because gluons carry the strong force charge, called color charge, they participate directly in these collisions. A gluon from one proton can scatter off a gluon from the other proton. A gluon can interact with a quark. These gluon-initiated processes produce specific patterns of outgoing particles that physicists can identify. By using polarized proton beams, where the proton spins are aligned in a known direction, and measuring how the collision rates depend on the spin orientation, experimenters can extract information about gluon polarization inside the proton. The facility that made this possible is the Relativistic Heavy Ion Collider, known as RHIC, located at Brookhaven National Laboratory on Long Island, New York. RHIC is the only high-energy collider in the world capable of colliding beams of polarized protons. It began polarized proton collisions in 2001, and over the following 2 decades, it produced a wealth of data on gluon spin. 2 major detector systems at RHIC, known as Phoenix and STAR, collected collision data across a range of energies and analyzed numerous types of outgoing particles. The technique works like this. 2 beams of polarized protons circulate in opposite directions around the collider ring and are brought into head-on collision at specific interaction points. The experimenters can choose whether the spins of the 2 beams are parallel or antiparallel. By comparing the rates of specific collision products between these 2 configurations, they can identify spin-dependent effects. If gluons inside the proton are polarized, certain collision products will be produced at slightly different rates depending on the proton's spin orientation. The size of this difference, called a spin asymmetry, is directly related to the degree of gluon polarization. Making this measurement work required solving one of the most formidable technical challenges in accelerator physics. Polarized protons are fragile objects in a collider. As a proton circulates around the ring, it passes through hundreds of magnets that bend and focus the beam. Each magnet exerts a force on the proton, and because the proton's spin interacts with magnetic fields, these magnets also exert torques on the spin. At certain specific energies, the spin precession induced by the magnets can resonate with the proton's orbital frequency around the ring. When this happens, the spin flips. The proton's spin, which was carefully aligned in one direction, suddenly reverses. As the beam is accelerated from low energy to collision energy, it must pass through dozens of these spin resonances. Each one threatens to depolarize the beam, randomly flipping spins and destroying the carefully prepared alignment. The solution is a device called a Siberian snake, invented by physicists Yaroslav Durbanev and Anatoly Kondratenko in the 1970s. A Siberian snake is a sequence of specialized magnets inserted into the accelerator ring that rotates each proton's spin by 180 degrees on every revolution around the ring. This rotation changes the conditions so that the destructive spin resonances cannot build up. The spin is flipped deliberately and coherently by the snake, which prevents the random, incoherent flipping that would destroy polarization. RHIC uses 2 full Siberian snakes in each of its 2 rings. These snakes, combined with careful orbit control and sophisticated feedback systems, allow RHIC to accelerate polarized protons from injection energy up to 255 billion electron volts per beam, while maintaining polarizations above 50%. At the collision points, additional magnets called spin rotators orient the proton spins into the desired direction for the experiment. By default, the Siberian snakes keep the spins pointing vertically, perpendicular to the plane of the accelerator ring. But some measurements are more sensitive to longitudinal polarization, where the spin points along the proton's direction of travel. The spin rotators can convert vertical polarization to longitudinal polarization and back, giving the experiments flexibility to optimize for different physics measurements. The entire system of snakes, rotators, polarimeters that continuously monitor the beam polarization, and feedback loops that correct for drifts represents decades of accelerator physics development. No other collider in the world has replicated this capability. It is one of the reasons RHIC's contribution to the proton spin puzzle has been irreplaceable. The measurements are subtle. The spin asymmetries are small, often just fractions of a percent. Extracting a reliable signal requires enormous amounts of data and painstaking analysis to control systematic uncertainties. But over many years of running, RHIC's experiments accumulated enough statistics to produce meaningful results. And the results were significant. The RHIC data, analyzed through a global fitting framework that combines data from multiple experiments, showed that gluon spins do carry a measurable fraction of the proton's spin. The best current estimates suggest that the net gluon spin contribution, meaning the total angular momentum from gluon spins after accounting for partial cancellations between gluons spinning in different directions, is comparable to the quark spin contribution. Different analyses give slightly different numbers, depending on assumptions made during the fitting process, but the central values cluster around 20 to 30% of the proton's total spin coming from gluon spins. This was a major discovery. It meant that gluons are not passive carriers of force sitting quietly inside the proton. They are active participants in the proton's spin budget. Their intrinsic angular momentum contributes meaningfully to the total. The strong force field itself carries spin. The proton's angular momentum is not just a property of its matter constituents, the quarks. It is partly a property of the force field that binds them, but there is an important caveat. The RHIC measurements cover a specific range of gluon momenta. Gluons inside the proton carry different fractions of the proton's total momentum. Some gluons carry a large fraction, meaning they are energetic and fast-moving relative to the proton. Others carry a tiny fraction, meaning they are low-energy, soft gluons. The RHIC data are most sensitive to gluons in the middle range. At very low momentum fractions, where there are enormous numbers of soft gluons, the measurements become much less precise. And the contribution from that low momentum region could be significant. Extrapolating from the measured region to the full range introduces uncertainties that are difficult to quantify. The true total gluon spin contribution could be somewhat larger or smaller than current estimates suggest. So gluon spin accounts for a sizable piece of the puzzle. Combined with quark spins, the two intrinsic spin contributions together probably account for roughly 50 to 60% of the proton's total spin. That is a substantial improvement over the original crisis, where quark spins alone seem to explain almost nothing. But it still leaves perhaps 40 to 50% unaccounted for, and that remaining fraction must come from the third and fourth terms in the spin budget. Orbital angular momentum. Orbital angular momentum is conceptually different from intrinsic spin. Spin is a property of a particle itself. It exists even in isolation, even for a particle sitting alone in otherwise empty space. An electron has spin 1/2, regardless of whether it is moving, regardless of where it is, regardless of what is happening around it. Spin is built in. Orbital angular momentum, by contrast, arises from motion. It is associated with the way a particle moves relative to some reference point. In classical physics, the simplest example is a planet orbiting a star. The planet has mass. It moves along a curved path around the star, and that circular or elliptical motion carries angular momentum. The amount depends on the planet's mass, its speed, and how far it is from the star. This is orbital angular momentum, and it is entirely separate from any spinning the planet might do on its own axis. Earth has both. It orbits the Sun, carrying orbital angular momentum, and it rotates on its axis, carrying what you might call spin angular momentum. The two are independent. They add together to give Earth's total angular momentum. Inside the proton, quarks also carry orbital angular momentum. But here is where the analogy with planets must be used with extreme caution. Quarks inside the proton are not orbiting a center point the way planets orbit a star. There is no neat elliptical track. There is no well-defined orbit in the classical sense. Quarks are quantum objects, and their behavior is described not by trajectories, but by wave functions, mathematical objects that encode the probability of finding the quark at any given position and with any given momentum. The quark does not follow a path. Instead, it exists as a spread-out probability distribution, a cloud of potential positions and momenta, with the actual outcome determined only when a measurement is made. Despite this, the concept of orbital angular momentum is perfectly well defined in quantum mechanics. A quantum particle confined to a small region and possessing momentum in a direction that is not purely radial, meaning not directly toward or away from the center, carries orbital angular momentum. The mathematics is precise. The values are quantized, just as spin is quantized. The orbital angular momentum quantum number takes integer values, 0, 1, 2, 3, and so on. The key difference from spin is that orbital angular momentum can be zero. A quark can exist in a state with no orbital angular momentum at all, a state where its probability distribution is spherically symmetric around the proton's center. This is called an S-wave state. In the simple quark model, the three valence quarks were assumed to be in S-wave states, carrying no orbital angular momentum. That assumption was part of what made the three-quark spin calculation so simple and clean. If the quarks carry no orbital angular momentum, then the only angular momentum is their spin, and the spin arithmetic gives 1/2. But the real proton is not that simple. The quarks inside the proton are confined to a region roughly 1 femtometer across. The uncertainty principle states that the more tightly a particle is confined in space, the larger its momentum must be. Quarks confined to a femtometer carry momenta corresponding to speeds that are a significant fraction of the speed of light. They are not sitting still. They are moving fast, bouncing around in a tiny volume, and the dynamics of the strong force give their wave functions complex shapes that can include non-zero orbital angular momentum components. The assumption that quarks sit in pure S-wave states was always a simplification. Quantum chromodynamics allows and even expects higher orbital angular momentum states to contribute. The same is true for gluons. Gluons inside the proton are not stationary. They move, they interact, they carry momentum in directions that are not purely radial. They too can carry orbital angular momentum, and since gluons are abundant inside the proton, their collective orbital angular momentum could be significant. So the full spin budget of the proton reads like this. Quark spins contribute roughly 30%. Gluon spins contribute roughly 20 to 30%. The remaining 40 to 50% comes from some combination of quark orbital angular momentum and gluon orbital angular momentum. These orbital terms are the least well-measured components of the spin budget. They are the frontier of current research. Why are the orbital terms so hard to measure? Because orbital angular momentum is not a local property. Spin is local. It is attached to a specific particle at a specific point. You can probe it by scattering a photon off that particle and seeing how the scattering depends on spin orientation. But orbital angular momentum depends on correlations between a particle's position and its momentum. It is not about what a quark is doing at a single instant. It is about the relationship between where the quark is and how it is moving. Measuring that relationship inside the proton requires knowing the quark's spatial distribution and momentum distribution simultaneously, and doing so with enough precision to extract the angular momentum content. This is extraordinarily difficult. Standard deep inelastic scattering tells you about the momentum distribution of quarks, what fraction of the proton's momentum each quark carries, but it tells you almost nothing about where those quarks are located spatially inside the proton. To access spatial information, you need different types of experiments. One crucial class of measurements involves processes called deeply virtual Compton scattering and deeply virtual meson production. In these reactions, the proton absorbs a virtual photon and emits a real photon or a meson, and the proton remains intact rather than being broken apart. The fact that the proton stays intact is essential. It means the measurement is sensitive to the coherent structure of the proton as a whole, including the spatial arrangement of its constituents. These exclusive processes allow experimenters to extract quantities called generalized parton distributions. These distributions are remarkable objects. They encode information about both the momentum and the spatial position of quarks and gluons inside the proton simultaneously. From generalized parton distributions, physicists can, in principle, calculate the total angular momentum carried by quarks of each flavor, including both their spin and their orbital contributions combined. The orbital contribution alone can then be obtained by subtracting the known spin part. This is the approach proposed by the physicist Shangdong Ji in 1997. He derived a sum rule, now known by his name, that connects the integral of certain generalized parton distributions to the total angular momentum of quarks. His result showed that if you could measure these distributions precisely enough, you could determine the quark orbital angular momentum contribution to the proton's spin. This was a theoretical breakthrough. It provided a roadmap for experiments, showing exactly what needed to be measured and how to extract the quantity of interest. But the measurements are incredibly challenging. Deeply virtual Compton scattering cross-sections are very small. The rates at which these reactions occur are much lower than ordinary deep inelastic scattering. You need high-intensity beams, large detectors, and long running times to collect enough data. The experiments that have been performed so far at facilities like the Thomas Jefferson National Accelerator Facility in Virginia have provided early constraints on generalized parton distributions. But the uncertainties are still large. We have hints, preliminary indications, but not yet precision measurements. Jefferson Lab is a Department of Energy national laboratory in Newport News, Virginia, built specifically for precision studies of the strong force. Its primary tool is a continuous electron beam accelerator that delivers electrons at energies up to 12 billion electron volts with extraordinary beam quality. What makes Jefferson Lab distinctive is not raw collision energy, but precision and intensity. Its electron beam is continuous rather than pulsed, meaning it delivers a steady, high-rate stream of electrons rather than brief bursts separated by gaps. This continuous delivery is ideal for the exclusive scattering measurements needed to access generalized parton distributions, because those reactions are rare and require accumulating large datasets over long-running periods. Jefferson Lab has been the world leader in these measurements for over a decade, and its experimental programs will provide essential groundwork for the Electron-Ion Collider that follows. There is also a deep theoretical subtlety lurking beneath this entire discussion. The decomposition of the proton's spin into four terms, quark spin, gluon spin, quark orbital angular momentum, and gluon orbital angular momentum, is not unique. There are different ways to define these individual contributions, and they give different answers for the separate terms, even though the total always adds up to 1/2. This might seem strange, even troubling. How can the quark orbital angular momentum be different depending on how you define it? The answer lies in a concept from quantum field theory called gauge invariance. Quantum chromodynamics is a gauge theory. This means its equations have a built-in redundancy. You can redescribe the fields using different mathematical conventions, called gauge transformations, without changing any physical prediction. All observable quantities, things you can actually measure in an experiment, are the same regardless of which gauge you choose. But some quantities that appear in intermediate calculations depend on the gauge choice. They are gauge dependent. It turns out that the individual terms in the proton spin decomposition can be gauge dependent. Different decomposition schemes define quark orbital angular momentum and gluon orbital angular momentum differently, and the values change depending on the mathematical convention used. Two prominent decomposition schemes exist. One, proposed by Jaffe and Manohar in 1990, separates the contributions in a way that is natural from the perspective of the underlying quantum fields, but where the individual gluon and quark orbital terms are gauge dependent. The other, based on the approach of Shangdong Ji, defines the contributions in a way that is gauge invariant for the total quark angular momentum and total gluon angular momentum, but divides quark angular momentum into spin and orbital pieces that are individually gauge invariant only in a specific gauge. This is not an error or a flaw. It reflects a genuine physical subtlety. Inside a strongly interacting system like the proton, separating quark and gluon contributions is inherently ambiguous at some level because quarks and gluons are constantly exchanging angular momentum through their interactions. A quark emits a gluon and transfers some angular momentum to the gluon field. A gluon splits into a quark-antiquark pair and transfers angular momentum back to the quark sector. These exchanges happen continuously, billions of times per second, in every proton in the universe. At any given instant, the boundary between quark angular momentum and gluon angular momentum is blurry, and how you draw that boundary depends on the theoretical framework you use. What is not ambiguous is the total. The proton's spin is 1/2, period. And any consistent decomposition scheme, applied correctly, will give individual terms that sum to 1/2. The subtlety is that comparing a quark orbital angular momentum number from one scheme with a gluon's spin number from a different scheme is not meaningful. You must use a consistent framework throughout. This theoretical complexity is one reason the proton spin puzzle has been so persistent. It is not enough to simply measure numbers. You must carefully define what those numbers mean within a specific theoretical framework. Experimentalists and theorists must speak the same language, and the language itself has subtleties that took years to fully appreciate. Despite these challenges, a coherent picture has been emerging. Let's summarize the current best understanding of the proton's spin budget while being honest about the uncertainties that remain. Quark spins contribute about 25 to 33%. This is the best measured component, established by decades of polarized deep inelastic scattering experiments across multiple facilities worldwide. The number is stable across different analyses and different experimental datasets. Gluon spins contribute about 20 to 30%. This is based primarily on data from RHIC, analyzed through global fitting frameworks that combine data from polarized proton collisions with data from polarized deep inelastic scattering. The central values vary somewhat between analyses, and the low momentum region introduces significant uncertainty. But the conclusion that gluon spin is a substantial contributor is now firm. Quark orbital angular momentum and gluon orbital angular momentum together make up the remaining 40 to 50%. These are the least well-determined components. Early constraints from deeply virtual Compton scattering experiments and from theoretical calculations suggest that both are non-zero, but the individual values are not yet precisely known. Some lattice quantum chromodynamics calculations, which simulate the strong force on supercomputers, suggest that quark orbital angular momentum may be a significant contributor, perhaps comparable in size to the quark spin contribution. But lattice calculations have their own systematic uncertainties, and different lattice groups sometimes get somewhat different answers. The challenges facing lattice calculations of proton spin are worth understanding in some detail, because they illustrate why even a theoretically exact approach requires extraordinary effort to produce precise answers. One major challenge is the signal-to-noise problem. The proton is a fermion, a half-integer spin particle, and fermion correlation functions on the lattice suffer from a peculiar pathology. The statistical noise in the calculation grows exponentially relative to the signal as you try to measure the proton's properties over larger time separations on the lattice. This means that extracting the ground state properties of the proton, disentangling its true quantum numbers from the excited states that contaminate the signal at short time separations, requires extremely large statistical samples. Modern lattice calculations use hundreds of thousands or even millions of independent gauge field configurations, each one representing a possible snapshot of the gluon field on the lattice, to beat down the noise. A second challenge involves the quarks themselves. In the real world, up and down quarks are very light. Their masses are only a few million electron volts, compared to the proton's mass of 938 million electron volts. Simulating very light quarks on the lattice is computationally expensive because light quarks produce long-range correlations that slow down the numerical algorithms. For many years, lattice calculations used quarks that were heavier than their physical values and then extrapolated the results down to the correct masses. This introduced systematic uncertainties that were difficult to quantify. In recent years, however, advances in algorithms and computing power have allowed several groups to perform calculations at or very near the physical quark masses, eliminating this source of uncertainty. A third challenge is the so-called disconnected diagram contribution. When computing how much spin the quarks carry, there are two types of contributions. Connected contributions involve the struck quark being directly linked to the proton's quark structure. Disconnected contributions involve quark-antiquark loops that are created and annihilated by the gluon field and are not directly connected to the valence quarks. These disconnected contributions are essential for correctly computing the strange quark spin contribution, since strange quarks exist only in the C. They are also important for the up and down C quarks. Calculating disconnected contributions is extremely noisy and computationally costly. Early lattice calculations simply omitted them. Modern calculations include them, but they remain the dominant source of statistical uncertainty in many lattice spin results. Dedicated techniques, such as stochastic estimation methods and variance reduction algorithms, have been developed specifically to handle disconnected diagrams more efficiently. Progress has been steady, and the precision of lattice spin calculations has improved dramatically over the past decade. The overall picture is that the proton's spin arises from a remarkably democratic distribution. No single source dominates overwhelmingly. Quark spins provide some, gluon spins provide some, the orbital motion of quarks provides some, the orbital motion of gluons provides some. The proton's spin is a collective property, emerging from the interplay of all its constituents. It is not located in any one place or carried by any one component. It is distributed across the entire quantum system. This is profoundly different from what physicists expected before 1988. The naive picture of three quarks carrying all the spin was simple, clean, and wrong. The real picture is messy, complex, and beautiful. The proton's spin emerges the same way the proton's mass emerges, not from the properties of individual quarks taken in isolation, but from the full dynamics of a strongly interacting quantum system. The quarks matter, the gluons matter, the motion matters, the force field matters. Everything inside the proton participates. There is something deeply revealing about this. The proton is one of the simplest composite particles in nature. It is made of quarks and gluons bound by the strong force. It is the building block of atomic nuclei, the foundation of visible matter. And yet, even this simplest of composite objects turns out to be extraordinarily complex on the inside. Its mass does not come from its quarks. Its spin does not come from its quarks. Both of its most basic properties emerge from the collective quantum dynamics of a violently active interior that is still, after decades of study, not fully understood. The proton spin puzzle is not a crisis in the sense of something broken. The physics is not failing. The theory of quantum chromodynamics is not wrong. The equations of the strong force almost certainly contain the complete answer. The challenge is that those equations are fantastically difficult to solve. The strong force is strong. The coupling between quarks and gluons is so intense that the usual mathematical techniques physicists use to solve problems in quantum field theory, techniques based on treating interactions as small corrections to a simpler picture, do not work for the strong force at the energy scales relevant inside the proton. The interactions are not small corrections. They are the dominant feature. This is what makes quantum chromodynamics so hard and so fascinating. The theory is believed to be correct, but extracting precise predictions from it requires either enormous computational resources or ingenious experimental approaches, or both. And that is exactly what the next generation of experiments is designed to provide. The proton spin puzzle has driven some of the most ambitious experiments in the history of nuclear and particle physics. Over the past 3 decades, physicists have attacked the problem from multiple directions simultaneously, using particle colliders, fixed target scattering experiments, and supercomputer simulations. Each approach reveals a different piece of the picture. None alone can solve the puzzle completely, but taken together, they are steadily closing in on a full accounting of where the proton's spin comes from. Let's start with the experimental programs that have shaped our current understanding, and then look ahead to the machine that many physicists believe will finally resolve the question. RHIC's polarized proton program ran for more than 2 decades, from 2001 until the facility began its transition toward the Electron-Ion Collider. Over that span, the program evolved substantially. Early running focused on establishing that gluon polarization was non-zero, a result that settled the most urgent question raised by the spin crisis. Later running pushed to higher precision and broader kinematic coverage, particularly at lower gluon momentum fractions, where the gluon density rises steeply and the contribution to the total spin integral is most uncertain. The final datasets from STAR, collected in the program's later years at the higher collision energy, provided the tightest constraints yet on gluon spin in the moderate to low momentum fraction regime. Throughout the program, RHIC's data were combined with measurements from polarized, deep inelastic scattering experiments worldwide. No single experiment can determine the full spin decomposition alone. Each experiment covers a different range of conditions and is sensitive to different combinations of quark and gluon properties. The power comes from combining them. By the time RHIC's polarized proton program concluded, the combined world data from RHIC, from COMPASS at CERN, from SLAC, from Jefferson Lab, and from DESI had been analyzed through what physicists call global quantum chromodynamics fits. These are massive computational analyses that take every relevant measurement from every experiment and simultaneously fit them within the framework of quantum chromodynamics to extract the best possible values for quark and gluon polarizations. Different research groups perform these fits independently, using somewhat different methodologies and assumptions, which provides a cross-check on the results. The global fits confirmed and sharpened the picture that had been building for years, with quark and gluon spins together accounting for roughly half to 60% of the total, and the remainder attributed to orbital angular momentum that existing experiments could only loosely constrain. While collider experiments like RHIC probe gluon spin through high-energy proton collisions, a complementary approach attacks the problem using the raw computational power of modern supercomputers. This approach is called lattice quantum chromodynamics, and it is one of the most remarkable achievements in theoretical physics. The equations of quantum chromodynamics describe how quarks and gluons interact. In principle, everything about the proton, its mass, its spin, its internal structure, follows from these equations. But solving them directly is fantastically difficult. The strong force is strong. The standard mathematical trick of treating interactions as small perturbations around a simpler system, a technique that works brilliantly for the electromagnetic and weak forces, fails for quantum chromodynamics at the energy scales relevant inside the proton. The coupling between quarks and gluons is too strong. Perturbation theory breaks down. Lattice quantum chromodynamics circumvents this problem through brute force. Instead of solving the equations analytically, which nobody knows how to do, physicists approximate space and time as a discrete grid, a lattice of points. They place the quark and gluon fields on this lattice and use the equations of quantum chromodynamics to calculate how these fields evolve and interact. The calculations are performed numerically on supercomputers, sampling billions of possible field configurations and computing averages over all of them using a technique called Monte Carlo simulation. The lattice serves the same purpose as the pixels on a screen. A photograph displayed on a screen is not a continuous image. It is made of discrete dots of color. If the dots are small enough and numerous enough, the image looks continuous and accurate. Similarly, if the lattice spacing is small enough and the lattice volume is large enough, the discrete simulation approximates continuous spacetime with high accuracy. Modern lattice calculations use lattice spacings of roughly 1/20th of a femtometer, meaning the grid is much finer than the proton itself. And they simulate volumes large enough that the proton can fit comfortably inside without being distorted by the boundaries. Lattice quantum chromodynamics has been spectacularly successful in predicting the proton's mass. Starting from the quark masses and the strength of the strong force as inputs, lattice calculations reproduce the measured proton mass to within a few % accuracy. This is an extraordinary validation. It confirms that quantum chromodynamics, solved non-perturbatively on a lattice, correctly describes the strong force dynamics that give rise to most of the proton's mass. If the lattice can get the mass right, there is strong reason to believe it can eventually get the spin decomposition right as well. And indeed, lattice groups around the world have been computing spin-related quantities for the proton with increasing precision. Calculating the quark spin contribution on the lattice is now fairly mature. The latest results confirm the experimental finding that quark spins contribute roughly 30%. This agreement between the lattice calculations and the experimental measurements is reassuring. It means the lattice methodology is working correctly for this quantity. Calculating the gluon spin contribution on the lattice is harder because gluon operators are noisier than quark operators in lattice simulations. The gluon field fluctuates more violently, creating larger statistical uncertainties. But progress has been substantial. Several lattice groups have published results for gluon spin, and while the uncertainties are larger than for quark spin, the numbers are broadly consistent with what RHIC measured. The most challenging lattice calculations involve orbital angular momentum. Computing orbital angular momentum requires knowing correlations between the position and momentum of quarks and gluons simultaneously, which is computationally demanding. Different lattice groups use different approaches. Some compute the total quark angular momentum, spin plus orbital combined, using the Shandong-Ji sum rule, and then subtract the known quark spin to get the orbital part. Others attempt direct calculations of orbital angular momentum operators. The results are still preliminary, with significant statistical and systematic uncertainties. But the trend is clear. Quark orbital angular momentum appears to be non-zero and positive, meaning quarks inside the proton carry meaningful orbital angular momentum that contributes to the total spin. Some lattice results suggest the quark orbital contribution might be comparable in size to the quark spin contribution, roughly 20 to 30%. If confirmed with higher precision, this would mean quarks contribute to the proton's spin in two distinct ways, through their intrinsic spin and through their motion, with both contributions being similarly important. Gluon orbital angular momentum is the least well-determined component. Lattice calculations of this quantity are in their early stages. The computational challenges are formidable. But in principle, once the other three contributions are precisely known, gluon orbital angular momentum can be obtained by subtraction. The total must equal 1/2. If you know 3 of the 4 terms, the 4th is determined. Now let's look ahead, because the most exciting chapter in the proton spin story has not yet been written. A machine is being built right now that many physicists believe will transform our understanding of the proton's internal structure more profoundly than any facility since the early days of deep inelastic scattering. It is called the Electron-Ion Collider, or EIC. The Electron-Ion Collider is under construction at Brookhaven National Laboratory on Long Island, the same site where RHIC has operated for over 2 decades. In fact, the EIC will reuse parts of RHIC's existing infrastructure, including the tunnel and some of the accelerator components. But it will be a fundamentally different machine. Instead of colliding protons with protons, the EIC will collide electrons with protons and with atomic nuclei. And it will do so with polarized beams at luminosities, meaning collision rates far exceeding anything previously achieved for electron-proton scattering. The EIC is not a proposal or a concept study. It is a fully approved and funded project. In late 2019, the United States Department of Energy formally approved the mission need for the project, a milestone known as Critical Decision Zero. Brookhaven National Laboratory was selected as the site shortly after, and detailed engineering and design work began immediately. The project represents the largest new construction in nuclear physics in the United States in decades, with a total cost estimated at several $billion. It is backed by an international collaboration of physicists from institutions around the world, many of whom have spent their entire careers working toward the measurements this machine will make possible. Why does this matter? Because electrons interact with quarks and gluons through the electromagnetic and weak forces, which are theoretically clean. The incoming electron exchanges a virtual photon or a weak boson with a quark or gluon inside the proton, and the resulting scattering event can be calculated with high precision within the standard model. There are no strong force complications in the initial interaction. The strong force governs what is happening inside the proton, but the probe itself is electromagnetic. This makes the interpretation of the data far cleaner than in proton-proton collisions, where both colliding objects are complex, strongly interacting systems, and disentangling who did what is enormously more difficult. The EIC is designed to measure the proton's internal structure with unprecedented precision across a vast range of kinematic conditions. It will collide electrons with energies up to about 18 billion electron volts against protons with energies up to about 275 billion electron volts. This gives center of mass energies ranging from roughly 30 to about 140 billion electron volts, covering a wide span of resolution scales and momentum fractions. And both beams will be polarized, with polarizations exceeding 70% for both the electrons and the protons. This combinations of high luminosity, wide kinematic coverage, and high polarization makes the EIC a precision spin microscope. It will measure quark spin contributions with far greater accuracy than existing experiments, extending measurements to higher and lower quark momentum fractions than previously accessible. It will provide the first precise measurements of gluon spin at low momentum fractions, the region where current data from RHIC are most uncertain and where the number of gluons is enormous. The gluon density at low momentum fractions rises steeply. There are far more soft gluons than hard gluons inside the proton. Whether these abundant soft gluons carry net spin is one of the most important open questions in the field, and the EIC is designed to answer it. Perhaps most importantly, the EIC will make precision measurements of deeply virtual Compton scattering and related exclusive processes that are sensitive to generalized parton distributions. These are the quantities that encode three-dimensional information about the proton, the correlations between position and momentum that determine orbital angular momentum. Current measurements of generalized parton distributions from Jefferson Lab and COMPASS are pioneering but limited in precision and kinematic range. The EIC will dramatically expand both. It will map out generalized parton distributions for different quark flavors across a broad range of conditions, enabling the first precise extraction of quark orbital angular momentum through the Shandong-Ji sum rule. The EIC will also measure a separate class of distributions called transverse momentum distributions. These encode information about how quarks and gluons are moving sideways inside the proton, perpendicular to the proton's direction of travel. Transverse momentum distributions are sensitive to the correlations between spin and orbital motion. They can reveal, for example, whether quarks tend to orbit in a particular direction when the proton's spin points up versus down. This provides complementary information about orbital angular momentum that cross-checks the generalized parton distribution approach. Here is an accessible way to think about what transverse momentum distributions reveal. Imagine you could take a snapshot of all the quarks inside a proton whose spin points upward. If the quarks had no orbital motion, their sideways momenta would be distributed symmetrically, equal numbers moving left and right, forward and backward. The distribution would be perfectly centered, showing no preference for any transverse direction. But if the quarks are orbiting, carrying genuine orbital angular momentum, the picture changes. Their sideways momentum distribution shifts. More quarks move in one transverse direction than the other, and the direction of that shift depends on the proton's spin orientation. Flip the proton's spin from up to down, and the asymmetry reverses. The preferred direction of sideways motion mirrors the spin flip exactly. This spin-dependent distortion of the transverse momentum pattern is a direct, unambiguous signature of orbital angular momentum at work inside the proton. The EIC will map these distortions across different quark flavors and across a wide range of momentum fractions, building a detailed and flavor-separated picture of how orbital motion correlates with spin for each type of quark and gluon inside the proton. Taken together, the EIC's measurements are expected to provide the first complete, high-precision picture of the proton's spin decomposition. For the first time, physicists will be able to simultaneously constrain all four contributions: quark spin, gluon spin, quark orbital angular momentum, and gluon orbital angular momentum within a single experimental program using consistent theoretical frameworks. This is not just incremental progress, it is a qualitative leap in capability. Construction of the EIC is expected to take roughly a decade, with first collisions anticipated in the early to mid-2030s. When it begins operating, it will open a new era in our understanding of the proton and of strongly interacting matter generally. It is not an exaggeration to say that the EIC is being built in large part because of the proton spin crisis. The questions raised by the EMC experiment in 1988 have driven an entire generation of experimental and theoretical work, and the EIC represents the culmination of that effort. But let's step back from the technical details and reflect on what this entire journey tells us about the nature of matter. The proton is one of the most common particles in the universe. There are roughly 10 to the 22nd protons in a single drop of water. Every star, every planet, every living organism on Earth is built from atoms whose nuclei contain protons. The proton is familiar, fundamental, and utterly ordinary. You would think that after a century of study, we would understand it completely, and in many ways, we do. We know its mass with extraordinary precision. We know its charge. We know its spin. We know its magnetic moment. We know its lifetime, which appears to be essentially infinite, longer than the current age of the universe by an unimaginably large factor. But understanding a particle's properties is not the same as understanding how those properties arise. And this is the lesson the proton spin puzzle teaches more clearly than almost anything else in modern physics. The proton has spin 1/2. That fact is simple, but explaining where that spin 1/2 comes from requires understanding the full quantum dynamics of a system of quarks and gluons interacting through the strongest force in nature. It requires knowing not just what particles are inside the proton, but how they move, how they interact, how they exchange angular momentum, how the force field itself contributes. It requires grappling with the fact that the proton is not a static object with fixed parts, but a seething, dynamic quantum system in which everything is connected to everything else through continuous, ultra-fast interactions. The proton's mass taught us the same lesson years earlier. As we saw, the quarks themselves account for almost none of the proton's weight. The overwhelming majority comes from the energy of the strong force binding them together. Mass is not something the proton inherits from its parts. It is something the proton's dynamics create. And now we know spin works the same way. It is not inherited from three quarks. It is generated by the full interacting system. Both of the proton's most basic properties, what it weighs and how it spins, emerge from dynamics, not from the intrinsic properties of constituents taken in isolation. The proton's spin does not simply sit on its quarks, waiting to be added up. It emerges from the collective angular momentum of the entire system. Quark spins contribute some, gluon spins contribute some. The orbital motion of quarks and gluons contributes the rest. No single component dominates. The proton's spin is a genuinely collective property, distributed across multiple types of angular momentum, carried by multiple types of particles, all entangled through the strong force into a single coherent quantum state. This is a profound insight into how nature works at its most fundamental level. The properties of composite objects do not simply inherit the properties of their parts. They emerge from the interactions between those parts. The whole is genuinely different from the sum of its components, not in some vague philosophical sense, but in a precise, measurable, physical sense. The proton has spin 1/2. Its quarks contribute about 30% of that spin through their intrinsic angular momentum. The rest comes from places the simple quark model never imagined. From the gluon field, from orbital motion, from the rich and violent quantum dynamics of the strong force. There is something humbling about this. We live in a universe built from protons. You are made of protons. The chair you sit in, the ground beneath you, the air you breathe, All of it is built from atoms held together by the electromagnetic force, whose nuclei are built from protons and neutrons held together by the strong force. And inside each of those protons, right now, at this very moment, the strong force is churning. Gluons are being created and absorbed. Quark-antiquark pairs are flickering into and out of existence. Angular momentum is being passed back and forth between quarks and gluons, between spin and orbital channels, in a ceaseless quantum dance that has been going on since the first protons formed in the early universe, less than a millionth of a second after the Big Bang. That dance produces spin 1/2, always, in every proton, everywhere, without exception. The internal dynamics are ferociously complex, but the outcome is perfectly precise. 1/2. This is the power of quantum mechanics. It does not merely tolerate complexity, it organizes it. The proton is not chaotic in the way a storm is chaotic. It is complex in the way a symphony is complex, many parts playing simultaneously, each contributing to a result that is exact, reproducible, and beautiful. And we are only now learning to hear all the instruments. The first deep inelastic scattering experiments at SLAC in the late 1960s revealed that quarks exist inside the proton. That was like hearing the melody for the first time. The EMC experiment in 1988 revealed that the melody does not explain the whole piece. There are harmonies, counterpoints, bass lines that carry just as much of the music. RHIC measured the gluon contribution. Jefferson Lab began probing the spatial structure. Lattice calculations are reproducing the dynamics from first principles on supercomputers. And the Electron-Ion Collider will give us the full score, every instrument, every voice, mapped out with precision for the first time. The proton spin puzzle is sometimes described as a crisis. And in 1988, it felt like one. The simple answer that everyone believed turned out to be wrong, and for a while, nobody knew what to replace it with. But in a deeper sense, it was not a crisis at all. It was a discovery. A discovery that the proton is richer, more complex, and more interesting than anyone had imagined. A discovery that the strong force, the most powerful force in nature, sculpts matter in ways that are subtle, surprising, and still not fully understood. A discovery that even the simplest building blocks of the physical world contain depths that we are only beginning to explore. And that is perhaps the most important thing to take away from this story. Not the numbers, not the percentages, not the details of which experiment measured what. Those numbers will be refined as better data arrive. The important thing is what they reveal about nature. That the properties of matter emerge from dynamics. That the forces between things matter as much as the things themselves. That the universe is more intricate, more interconnected, and more astonishing at its foundations than any simple picture could capture. Every atom in your body contains protons. Every proton carries spin 1/2. And that spin arises from the full quantum symphony of quarks and gluons, spinning and orbiting and interacting through the strongest force in existence, inside a volume smaller than a trillionth of a centimeter. That is what you are made of. That is what everything is made of. And we are still, after all these decades, learning exactly how it works. The next time someone tells you a proton is just 3 quarks, remember this story. Remember that less than 2% of its mass comes from those quarks. Remember that less than a third of its spin comes from their spinning. Remember that the proton is a storm of quantum fields, gluons and quarks moving at nearly the speed of light, exchanging angular momentum in a dance so fast and so complex that it has taken the most powerful accelerators and the largest supercomputers on Earth more than 30 years to begin unraveling it. And remember that the machine being built right now on Long Island is designed to finish that job, to give us at last the complete picture of how the proton gets its spin. That picture, when it arrives, will be one of the great achievements of 21st century physics. Not because the answer will be simple, it will not be, but because it will show us, in precise, quantitative detail, how the strong force builds the most basic unit of visible matter from quantum fields. How mass and spin and structure emerge from the interactions of quarks and gluons bound together more tightly than anything else in nature. The proton is small, it is common, it is everywhere, and it is, even now, not fully understood. That is not a failure of physics. That is what makes physics worth doing.